So let's talk about k-means from a more mathematical perspective. The input to k-means is your data set, and then the number of clusters you're going to have. And the output is just the centers of the clusters. And those cluster centers are chosen to try to minimize something or other. And what is that? So it starts with the distance between a point, xi, and a cluster center, ck. Now, we want to use the nearest cluster center, the cluster center with the minimum distance to u. And then we want to sum all those distances up. Okay, so we want the total distances to the nearest cluster center. And again, we're trying to find the cluster centers that minimize cluster centers that minimize the total distance to the nearest cluster center. Okay, so this thing here, this is a global objective. But you see, k-means, it actually has local moves. It's trying to optimize this, but it can't optimize the whole thing at once, like, support vector machines or logistic regression or anything. It would be really nice if we could just plain globally optimize this. Okay, so why the heck not? Why can't we just globally optimize this over all cluster centers? Well, the problem is that we can't even figure out what assignments to make for the clusters, because we could try all possible assignments, say of m points to k cluster, and this would be great if we had only 10 points and 4 clusters, right? Because that would be only 34,000 possibilities, and we could easily run through all of them. But if we had 19 points and 4 clusters, well, that's 10 to the 10th possibilities, and that's yucky, and we can't compute that many possibilities. So k-means is an approximation. It cannot optimize this thing. It can't, because it can't even figure out what the assignments are. Now, I want to take a look at that cost function again. Now, I want to take a look at this cost function again. It's a sum over the points of the distance to the nearest cluster center. It's just adding up all the points one by one. So I can count the points. I can count the points this way. I can just sum them all up. I can count them from left to right or something. So that's one way to count them up. That's why they're all turning red like this from left to right, because I'm counting them in that direction. But I could simply try to sum them up in a different order, right? So all I did here, the sum didn't change. I just wrote it differently so I could sum things up in a different order. So here I'm still summing over all the points, but I'm first summing over clusters and then summing over the points in each cluster, right? So sum up over cluster 1's points and then over cluster 2's points. And that's the only change I made there. Now let's try a slightly more general cost, because I want us to optimize who is assigned to what cluster, okay? So I'm going to put the cluster assignments here as well as the cluster centers. So cluster 1, this is all the points that are assigned to cluster, the first cluster. And then these are all the points assigned to the second cluster and so on. And these are the cluster centers as before. And now because I wrote the cost function like this, the CKs, they're no longer forced to be the center of the clusters, right? We're going to make them to be the centers of the clusters, but I want to call them reference points for now, because this function is actually so general that can allow any points to be assigned to any cluster whose reference point can be literally anywhere, right? It doesn't have to be in the center. Okay, so this is a cost function of both the cluster assignments, so who's assigned to what cluster, and what we're going to use as the reference points for the clusters. And we want to be able to change these things around independently of each other and evaluate the cost. So let's just look at this cost as if it's a function of the cluster assignments only. Now, if we fix these CKs, fix the reference points, what's the best way to assign the clusters, assuming you fix the centers? And the answer is obvious. You just assign the points to their nearest cluster center, okay? And that's exactly what k-means does. Okay, so you just assign the points to the nearest cluster center. Okay, so on the other hand, what about assigning the reference points? Right? If we have the cluster assignment set, where should we put the reference points? And of course, we would try to minimize the cost by putting those in the center to minimize the average distance to the reference points. And that's exactly what k-means does. Okay, so now you should have a much better understanding of what k-means is actually doing. So I'm going to put the cost up here just for reference. And remember that it depends on both the cluster assignments and the cluster centers. And now let's put up the algorithm again. So until you're converged, you just assign all points to their closest cluster center. And that's the same thing as minimizing the cost by choosing the best assignments given the cluster centers. And then for the next step, you change the reference points so that they're actually in the center of the points assigned to those clusters. And this minimizes the cost of those reference points, fixing those cluster assignments. So k-means is sort of an alternating minimization scheme. First it's minimizing the cost over the cluster assignments, then it's minimizing the cost over the cluster centers. So it's alternating between the two. So we call it alternating minimization. So now here's a question for you. Given that k-means' actual goal is to minimize this cost, does it actually achieve this goal? We know that the cost gets lower at each step of k-means because you're always minimizing. But does it always converge to the globally optimal set of cluster assignments and reference points? And the answer is not always. You might actually need to, restart it and do multiple replicates. Because if you happen to start the reference points off in a bad spot, sometimes it just won't go to the right place. And that's why most k-means code allows you to do replicates, so you can start with different randomly chosen points to be the centers. Now there's something even worse than that, because k-means' goal might not be the right one, right? This cost function, that might not actually be the thing you should optimize to get the best clusters. So let me show you an example where this objective is just plain wrong, okay? No matter how you set up the initial cluster centers, you're going to get garbage. Okay, so, all right, there's the initial cluster centers. These two guys are at the top. They're going to separate a bit. Keep an eye on those two. So there's the first iteration, and we'll keep going. Beautiful, huh? Just doing nothing. And then it calls itself converged at this point. Black. Anyway, you can find some, so you can find examples where k-means doesn't optimize its objective function. Here it did a good job of optimizing the objective. It's just that the objective was really lousy for this data set. But anyway, it's a nifty little algorithm, and it's very heavily used, and now you know what it's doing. Okay, so let's discuss a bit more about practical aspects of k-means, and in particular, how you're going to choose k, because you have to put k in as an input. Now, there's a couple of options. There's no single right answer for this, but one option is to look for the point of diminishing returns. So as you increase the number of clusters, the cost function is going to go down, but after a while, it won't go down very much. And that's probably where you want to stop. Like, this is the point of diminishing returns. The more cluster centers you have here, it's not lowering your cost very much. So you might want to stop there where the kink in the curve is. So option one, look for the point of diminishing returns. Another option is to look at the ratio of the average distance to your assigned cluster center versus the average distance to the other centers. For the average distance to your assigned center, you just compute the distances to the assigned center, the closest one, and then you compare that to the average of the distances to the other centers. Now you kind of want these numbers to look very different from each other. Ideally, you want to have nice tight clusters that are far away from other clusters. So if the first one is small and the second one is large, that's good. Now, if you put too many cluster centers in there, both of these things are going to decrease. Both distances will decrease, but you still want them to be kind of as far apart as possible. And to be honest, I don't really like this metric, right? It's fine for 2 clusters, but not really for more than that. So I actually think this average distance to other centers should be replaced with the average distance to the center that's not yours, but is the closest other center. Well, I didn't design this software, so it's not my fault there. But anyway, so that's my opinion on this metric. This one's not particularly good. I'd much rather use the kink in the plot. All right, so k-means, just to summarize, it's a popular clustering algorithm. It is very computationally efficient because finding the mean of a bunch of points is easy, and then it's a single loop to find out what the cluster assignments are. It performs alternating minimization on a cost function, and I showed you exactly what that cost function was and what the alternating minimization scheme was. Now, it doesn't always fully minimize that cost function, and so multiple replicates with different initial conditions, different initial centers, might be needed to find a good solution. And you can actually use the cost function itself to evaluate whether one replicate is better than the other, because you'll get a lower cost if it's better. And then you can also use that cost function to help you choose that number of clusters by looking at that kink in that plot, the cost over number of clusters. Now, as I showed you in that example, it doesn't really work for non-spherical clusters, but it works very nicely when the clusters are actually spherical.